My name is Philip Stier, and I'm be chairing today's session with Bill Collins from Berkeley that we're very much looking forward to. To introduce Bill, he received his undergraduate degree in physics from Princeton, did then a PhD in astronomy at the University of Chicago, then joined the National Center for Atmospheric Research, where he was one of the lead climate scientists and lead climate modelers for quite some time. And then he joined Berkeley and Berkeley Lab, where he's now Associate Lab Director for Earth and Environmental Sciences, and also professor at the university in the Department for Earth and Planetary Science. But as many of us, Bill has wandered more and more across the interface of climate and AI, including hosting a fantastic workshop in Aspen on this topic last year. And today, Bill will speak on a really interesting topic, the use of really fast surrogate models for huge ensembles of weather extremes. And I'm very much looking forward to your talk. Over to you, Bill.
Thank you so much, Philip, for the introduction, and it's a pleasure to be here. Let me start sharing my screen with all of you. So, yes, thank you so much for the opportunity to describe some work that we are launching with colleagues both here at Berkeley and also just on the road from us at Nvidia on constructing huge ensembles of weather extremes using a tool that Nvidia has developed called the Fourier Forecasting Neural Network, or FourCastNet. And this talk really would not have been possible without the team of people who've been working on this project. As you can see, they span Nvidia, as well as contributors from Caltech, Purdue, University of Michigan, Rice, and also Lawrence Berkeley Laboratory. And I'll be drawing on slides contributed by Karthik, by Mike Pritchard, by Peter Harrington during this presentation to you. And it really would not have been possible without their very generous loaning of slides to me to make this possible. So as I mentioned at the top of this presentation, we're going to be focused on something known as low likelihood, high impact extremes, or LLHIs. These were discussed extensively during the and in the 6th IPCC assessment report, particularly because they have significant and usually dire impacts on both society and the environment. And I'll describe sort of a framework for understanding what causes them, and that will then drive me directly to the need to use data-driven forecasting in order to understand these extremes. I'll then discuss why we think that the FourCastNet model is particularly suitable for this application, and describe a little bit of its architecture and why it does so well, for example, on precipitating extreme storms, hurricanes, and so forth. And then discuss ongoing and future work that's underway by our colleagues at Nvidia, as well as here at Berkeley Lab, on extending the duration of forecasts and hindcasts, and also increasing the throughput. Then I'll conclude and take any questions that you might have. So a number of us were involved in the 6th IPCC assessment report, or AR6, the Working Group 1 report, which concerns the physics of climate change, was issued in August of 2021. And it said in one of its numerous statements that the future occurrence of these low likelihood, high impact events linked to climate extremes is generally associated with low confidence. In other words, we're not quite sure what's going to happen, but cannot be excluded, especially at global warming levels above 4 degrees Celsius. And these events, and we've just been experiencing some here in California, range all the way from heat waves to atmospheric rivers, what drives the hydrological cycle here on the west coast of the United States, tropical cyclones and extratropical cyclones, other types of extreme precipitation events, co-occurring extremes, and also droughts, decreases in mountain snow. And I'm well aware that Europe has been experiencing precipitous drops in snowfall this past winter. So we're very interested in these events because they can have appreciable impacts on both our infrastructure and also on the natural environment around us. And to give you a couple of examples, And I'm sorry to be parochial, both of these will be from the United States. The first is from a Pacific Northwest heat wave that occurred in 2021 in the Pacific Northwest, where temperatures over portions of that region approached, if not exceeded, 40 to 45 degrees Celsius. It was really unusually warm for us in this portion of the United States, and was a sort of a record-breaking event, one for which the Seattle metropolitan area is very unsuited because very few people in Seattle and in Vancouver have air conditioning, a condition that's also shared by many people in Europe who've enjoyed historically temperate climates. Similarly, we've been going through quite a set of atmospheric rivers this winter and spring, winter just leading up to spring. By the time we'd gotten through January, we'd already experienced here in California $40 billion in economic impact, and it had both federal and state emergencies declared. And you can see these are pictures taken in January of some communities in Central California that were flooded, whole sets of highways shut down. At this point, large portions of the most productive agricultural land in the Central Valley is flooded due to these atmospheric rivers. So they're events of intense interest. So what the assessment report said is that these outcomes or events cannot be ruled out and are part of any logical risk assessment. They come with potentially very large impacts, and their probability increases with higher global warming levels. We're confident about that, but we're not really confident about actually quantifying the probability. And I lead a project here at Berkeley Laboratory that's devoted to looking at extremes, and we've decided to devote the next 3 to 5 years of that project to looking at these types of events and really focusing in on what causes them. What I'd like to do now is describe a little bit of a conceptual framework for how to tackle this problem, because remember, these are low likelihoods. We don't have a lot of samples of them in the historical climate record. And so we need a means for studying them that isn't hinging or contingent on finding a needle in a haystack. And so one way to do that is to use machine learning causal inference to switch from looking at an extreme event E, shown here in the diagram in blue, to the drivers of that event, shown as D1 through Dn. And if you assume that you can use machine learning causal inference, for example, graphical techniques, to uncover the drivers, and those drivers have moderately low probability, but not vanishingly small, then if you also use, for starters, just a null hypothesis that the recurrence probability of the event is the joint probability of each of the drivers occurring randomly on top of each other, then you can easily construct very low likelihood events with probabilities much less than 1 from drivers that actually have a reasonably high recurrence time. And what that means is that if you switch from studying the event itself to the drivers, you can study the drivers in exquisite detail using the historical climate record. And in fact, in many cases, we have theory for how those drivers should change in a warmer environment. So this becomes a real game changer. The idea is to pivot from looking at the event to its drivers. And of course, we can depart from this simple null hypothesis for the recurrence probability. And I won't have time to cover that in any great detail, but that's certainly a possibility. So the idea here is that due to the finite recurrence time of these drivers, it's much easier to study them. Relatively short observational or simulated time series are required. You can begin then to ask what is really driving changes in the recurrence probability of the extreme event by looking at the sensitivity of the recurrence probabilities of the drivers themselves, and then isolate the most important drivers that are changing due to anthropogenic climate change or varying due to natural fluctuations in the climate system, such as ENSO. So this, again, becomes a powerful conceptual framework for studying the origin of these extreme events in the climate record. And then we can also compare these drivers to climate models and ask, do the climate models also reproduce these drivers? Do they have the same measures? So this also becomes a technique for diagnosing climate models, which is quite handy. So some of the other goals here are to think about possibly using this framework to begin doing rapid attribution. And we have not yet contacted the world weather attribution groups. There's a local outfit, for example, at Oxford, but that could be an aspiration for us and could be a quite interesting effort. If we can understand the drivers, then we can do attribution just about as rapidly as numerical weather prediction, in fact, faster. So this becomes a means for doing rapid detection and attribution, asking whether events that occur, and we can use them to interpret experiments that show up in future climate assessments, what are known as storyline and pseudo global warming experiments. And I think aside from just the climate science that I've been describing here, this will provide us with a means of really elevating the confidence of the statements that we're able to make, hopefully, in future IPCC assessments like the 7th assessment, which will be booting up in the next few years. And so one of our aspirations is to really put our confidence about the science behind extremes and then the knock-on effects that show up in the 2nd assessment report having to do with the impacts of climate change, and the 3rd assessment report, which deals with how to mitigate the effects of climate change, to put all of that in a much more solid footing. Good. Well, the context for our knowledge about extremes so far that isn't based solely on observation records comes from weather forecasting and from climate models. And the numerical weather prediction community has come quite a long way from its inception. Computers are now literally 1 trillion times faster than the machines that Suki Manabe used to win the Nobel Prize. So that's quite an increase in compute power over the last 4.5 decades. And we now have enterprises running worldwide solving the Euler Equation Set to understand how weather will evolve in space and in time. And the equation sets for these things are at their heart fairly simple. They consist of 3 core equations that concern conservation laws from physics, conservation of momentum, energy, and mass. But then because of processes operating in the Earth's atmosphere, those equation sets become considerably more complicated, and we run them on grids over the globe that are now approaching the length scale of individual cities. So for example, San Francisco is 120 square kilometers. Modern numerical weather prediction is now approaching those length scales. So that's really quite an achievement for this community. And it consumes a gigantic amount of compute power. The challenge for us, though, is that these models are not fast enough to do what I think we need to do to look at extremes. And it's for this reason that I've been in conversation with colleagues at Nvidia about a new approach going forward, which would get us out of this very slow evolution of forecast skill you can see in this graph. So the models have been getting steadily better. And this, again, is quite a remarkable attainment by the numerical weather prediction community. The lowest trace in this graph is 10-day forecasts for the southern and northern hemisphere. And the skill of those has been steadily increasing over time. This is really a remarkable achievement, but I'm sorry to say that it's not going to be fit for purpose. And it's for this reason that we've been talking to colleagues in the machine learning community about emulating numerical weather prediction using machine learning. We are fortunate that we can train these machine learning algorithms on the historical climate record, which now runs to nearly 15,000 days since the start of the modern satellite record in 1979. These models are small enough and agile enough that they can be stood up by relatively small teams in tech companies or by individual computer centers. The code I'm going to describe here is entirely in the public domain. And their skill is rapidly progressing. In fact, since we started this conversation, the skill of this particular model has gone from it's been able to make skillful forecasts for 4 days up to now nearly an order and a half magnitude larger length scale, time scales than that. So they're rapidly evolving in time, much more rapidly than numerical weather prediction. The tool I'm going to describe to you today is the basis for the work that we're launching with Nvidia around huge ensembles is called ForecastNet. And what I'd like to do is talk about what it does before I talk about the model itself. And to place it in context, this is a time series to scale of our ability to emulate the climate record using machine learning of various flavors up to the present day. And you can see that that's ranged over essentially 2 orders of magnitude in pixels, again, on very short timescales. So essentially starting from 2018, 5 years later, we've increased the horizontal resolution by a factor of 100 in the number of pixels, a factor of 10 in length and width, again, vastly exceeding the growth rate of numerical weather prediction. So machine learning is on a growth path that is completely uncharacteristic of what we've been used to traditionally. And ForecastNet turns out to have some very nice properties. It's a global model. It's a full surrogate for the atmosphere. So it simulates wind fields, moisture fields, pressure fields, precipitation fields. It's based on a technique that I'll come back to a little bit later called a Fourier neural operator plus a transformer. And the Fourier technique that's embedded inside ForecastNet is really key to its ability to be sort of agnostic about resolution and has allowed it to span a variety of resolutions very quickly. It's currently operating at a resolution and is being trained at a resolution of 25 kilometers based on reanalysis from the European Center for Medium Range Forecasting. And it's able to do a 2-week forecast in half a second. And that's really the key to our ability to generate ultra-large forecasts. I currently have a grant proposal in with Nvidia to get 300,000 node hours on a supercomputer here on GPU nodes. So if you, translate that into we will be able to do 500 million 2-week forecasts with that computer allocation, just to give you some sense of the scale of that's enabled by the speed of this system. It uses a variety of techniques to calibrate itself. It's roughly 100,000 times faster than numerical weather prediction, saves a factor of 10,000 on the power consumption to produce the same level of fidelity. And it's now able to, as I mentioned earlier, it's gone from roughly a week now to close to a year in terms of being able to produce reliable, stable forecasts of climate. And it's open source. So for simulating the extremes, this is essentially a killer app, right? It allows us, so we're looking at events that have recurrence times of 1 in 10,000 to 1 in 100,000 per unit time. So we're interested in extremely strong rainfall events. The fact that we're able to construct very large ensembles means that we can recreate, for example, the last 2 weeks of weather globally, perturb it slightly, and then look across an ensemble of tens to hundreds of thousands of ensemble members and ask, does one of them produce an extreme? And what this allows us to do then is to go in and look at that extreme, understand its drivers, going back to that conceptual framework I described to you a little bit earlier, and drive exquisite statistics on what causes these extremes from accurate emulation, slightly perturbed, of the historical climate record. And it's because of its ability to generate ultra-large ensembles extremely rapidly that I'm calling ForecastNet a killer app in this context. So I came up, there's a group at NCAR that, along with other colleagues worldwide, launched LENS, which stands for Large Ensemble. And I was trying to think of something cute to name this ensemble. So I decided to call it HENS for Huge Ensemble of 10 to the n members, where n is greater than or equal to 4, in order to converge statistics. I've played around with stable diffusion to generate cartoons of a hen sitting on top of an Everest of eggs. I won't embarrass you by showing the cartoons that came out of stable diffusion. but I do have one on my desktop in case that comes up during the question and answer period. But yes, Stable Diffusion is able to now produce cartoons at will that are pure and amusing if you have some spare time. So I'm looking for the perfect logo for this project at the moment. So what does FourCastNet do? It's emulating, as I mentioned, it's trained on and is able to emulate wind fields. This is an example of its ability to emulate wind fields with lead times of 18, 36, 54, and 72 hours, up to 3 days. And the ERA5 is shown on the, again, which it should be emulating, is shown on the lower row, and FourCastNet is shown on the upper row of this graph. The colors are in meters per second of wind speed. And you can see that it's able to accurately place major storm and frontal systems across the continental United States. Again, sorry for this presentation being slightly parochial, but everyone who's working on it locally is based in California. So, but this does work globally. As illustrated in this graph, where if we look at the behavior of wind fields, and now we're able to look at a variety of storms, this is looking at a set of tropical cyclones and hurricanes. It's able to emulate wind fields and reproduce circulating systems in the climate system up to 4 days accurately. And so the upper part of this graph, the upper row is the initial conditions, and then you ask how well does FourCastNet 4 days later emulate rotating circulating systems, and you can see it places them correctly in the Atlantic Basin. And that's shown in the right-hand column, where FourCastNet is correctly situated Florence, Isaac, and Helene relative to their positions in the ERA5 analysis. So for the standpoint of emulating low likelihood, high impact events, for example, Category 5 or even Category 6 hurricanes, this looks like it could be quite promising. And of course, there's now efforts underway to understand how well it's able to emulate hurricane tracks. It's another very important feature of this system. I'll come back to that a little bit later. It's also able to emulate moisture fields in quite exquisite detail. And we have been, of course, very interested here in California in looking at the impact of atmospheric rivers. It's able to do those. And the box here, the upper box on the upper right-hand side of this figure is showing the incidence of atmospheric rivers on the west coast of California. Ground truth is the bottom row. FourCastNet is the upper row. It's also able to look at the rivers impinging on South America, on Europe. And of course, these atmospheric rivers are pervasive features in both hemispheres. And the colors here are showing you color integrated water vapor amount, which is a commonly used measure to track atmospheric rivers in numerical weather prediction and also in observations of the climate system. One of the features that we have been particularly interested in my project has been extreme rainfall. And this is where my colleagues at Berkeley Laboratory were able to contribute to the work being done by Nvidia to add fidelity. So the team led by Peter Harrington here went in and took the network, this neural network that was constructed by Nvidia, and added to it a GANs, or generative adversarial network, to improve the fidelity of the precipitation coming out of the FourCastNet. And their starting point is the graph in the upper right, which shows the total precipitation percentile versus the amount of rainfall falling. So for example, the 99.9th percentile rainfall event is generating approximately 25 millimeters of rainfall or snowfall during that event. The 99.99th is generating nearly 50 millimeters of rainfall. And as you can see, the ERA5 is generating appreciably more rainfall than the FourCastNet before my colleagues here at Berkeley Laboratory went in and began adding feature sets to FourCastNet. And what they were able to do is use adversarial training to increase the resolution and also increase the fidelity of the distributions of rainfall coming out of the model. And so the new result is now shown in the right-hand graph, where again, ERA 5 is the black dotted line. And the L1 plus adversarial, this is the new version of FourCastNet. So the original FourCastNet is the sort of the puce trace, the lowest trace on this graph. And the red trace, the L1 plus adversarial, is the new version of the system once the GANs have been added. And it brings the amount of rainfall for the most extreme events much closer to that from the reanalysis, which is what we want. And they've also added noise into the network, which is another key feature, because we want this huge ensemble to actually not, we don't want it to be deterministic. So it's very important that the system have carefully injected noise so that the system is both, exhibits the appropriate error growth with time. I'll come back to that point in just a moment. So the system is deliberately designed to not be deterministic. And I'll show you that it, in fact, emulates the error growth that we see in the reanalysis in just a few graphs from here. So the result is that we're now able to, this is now millimeters of rainfalls. This is similar to the graph I showed you earlier for wind speed, but it's now the rainfall amount over the globe, again, with the initial condition in the upper row of this figure, and then the precipitation with a lead time of 36 hours in the middle from FourCastNet, and ERA 5, the training data set on the lower graph. And we've honed in on some atmospheric rivers that are just about to impinge on the west coast of California and also on Europe with the red and pink boxes. And the on the right-hand column shows the fidelity of the rivers that are just about to hit Europe in this particular emulation of the weather from a couple of years ago. Okay, so we covered this point. For the purposes of low likelihood, high impact events, we're very interested in generating large ensembles. As I mentioned, this is now trivial. Our work so far, and I'm not going to show you much of what we've attained so far, but we were able to easily generate ensembles of 100 members in a little under a minute on the hardware that we have available here at Berkeley Laboratory. And our goal is to increase that once we understand the multi-ensemble characteristics of that ensemble. So we want to make sure that it's exhibiting the proper error growth, the proper ergodicity, and actually after 10 days, the growth of chaotic modes. Once you understand those behaviors, then we'll start running ultra-large ensembles. But we're at a very exciting time here with being able to look both at the historical record and also the future. So I've also started work with Nvidia on using the high-res-MIP, or high-resolution modeling or comparison project, that was constructed for the sixth assessment report. High-res-MIP followed some of the ensembles shown on the right-hand side for global warming out to the year 2050, but it saved the data at both conventional and also quite high model resolutions, 25 degrees, which is high for a climate model, with high temporal resolution of 6 hours. And I have I've constructed a copy of the high temporal frequency data from high-res-MIP here at Berkeley Laboratory, thanks to a collaboration with the colleagues in the UK at RAL, who were very generous in providing me with data from the small collection of high-res-MIP that they ran in Europe, along with data assembled from the Earth System Grid. I'd be happy to share that information with anyone on this today's seminar who would like to use it. It's freely available to the global climate community, and it's very useful for training machine learning algorithms. So we're now working with them on training FourCastNet to look into the future and see if we can emulate global warming signals. So that's something else that we have underway with them. So what is FourCastNet? it is a null operator. It's hard, and the key feature of the null operator is that it operates in Fourier space, and it's essentially a Fourier it uses the Fourier convolution theorem to emulate, in effect, the Green's function for the Clement system. So if you were to imagine looking at the solution to the Euler equations and imagine describing them with an effective Green's function, the FourCastNet is training off of the Fourier transform of that Green's function, and that has the advantage that it's looking at essentially the propagation operator for the Clement system. So it's not emulating off of emergent behavior; it's operating off of the transform that evolves the Clement system into the future. Also, because it's operating in Fourier space, it's very resolution agnostic. So it's not operating on the projection into real space; it's operating in wave number space, which means that, of course, it is truncating in wave number space, but this does provide it the ability to go to much higher resolution. And in fact, Nvidia has shown that coupling FourCastNet to some other post-processing algorithms allows it to attain resolutions up to 10 times higher than the training data set, which is quite remarkable. And it's currently the highest resolution data-based global weather model to date. It's trained off of wind fields currently, so approximately 26 different fields: wind fields of the surface, mean sea level pressure, fields aloft, along with geopotential height, total column water vapor. And then we ask it to then predict rainfall and so forth. But at its heart, it's really looking at the prognostic fields coming out of the Euler equations and training off of those prognostic fields. That's how it's trained. And as mentioned on this slide, it's trained with approximately 26 years worth of data and then validated on the recent historical past, and then tested against data for the last 5 years, from 2018 onwards. And so the tests that I've shown you have been based on the very recent historical past. So how does it do in terms of its skill? So this is the way that the numerical weather prediction community, one of the many ways that it looks at the fidelity of their models. And the training standard is shown in yellow on this graph. And ACC here is the anomaly correlation as a function of time. And what you'd like to see is that the model remains, essentially it's able to produce very faithful, very high anomaly correlations that extend as far out as possible from the initialization time, which is 0 on the horizontal axis on this graph. And as you can see, the meteorological standard maintains quite good skill, up to 80% correlation out to forecast times of approaching 10 days. And the FourCastNet is coming close to, if not approaching that skill currently, which is quite good for both 500 hectopascal geopotential height and 10 meter surface winds. The other thing that I mentioned to you that's very important that the network do is exhibit error growth, because remember, if we're looking at the reason for generating an ultra-large ensemble is that we want the different members of that ensemble to differ from each other. And so we need for there to be error growth. In other words, the system needs to be appropriately sensitive to the introduction of infinitesimally small noise, because as we know, the Euler equations have positive Lyapunov modes. So the error growth should grow with time. And in fact, as shown in this graph, if you look at numerical weather prediction models, and compare them, the UK Met Office model, the European Centre medium range forecast models, they all exhibit, and NSAP, they all exhibit error growth as a function of time, as does the FourCastNet. So it's tracking the error growth that we expect from numerical weather prediction, and this is a feature that we really want in order for an ultra-large ensemble to be sort of a mine, where one member in, say, 10,000 will exhibit behaviors that the other 9,999 don't. And so this is this property, along with the growth of chaotic modes, is a really important part of the system, and is something that Mike Pritchett and their colleagues are actively investigating to make sure that the model does in fact exhibit these growing modes. And I mentioned earlier, and this is a quote from Bjorn Stevens, the idea is that one of the challenges we're going to face with this system is that it will be generating data so fast that we can't save it all. And so we will be looking at it in snapshots. When I say we can't save it all, the backbone of the supercomputers that we have currently, the communications backbone, the network, isn't sufficiently fast to save all the state information coming out of an ultra-large ensemble. And so, as Bjorn realized, we will be looking at snapshots of the system in time. And one possibility that we're exploring is the idea of running diagnostics in line with the system. So we essentially decide what we want to archive and save it as the model evolves. This, again, is a very different mode of operating from the climate community. The climate community is used to savoring every bit. And in fact, that's the to first approximation how the climate community has operated for the last 55 years, because it was very expensive to rerun a model. But imagine a world in which it's actually much cheaper to rerun the model than it is to save the data. That's a radically different world, and that's the world into which we are now moving. And so what we're going to do is run this code on GPUs. We'll also be running the diagnostics in massively parallel mode on GPUs. So we'll be moving the climate community into a mode that looks a lot more like the way that the Large Hadron Collider works, where most of the data coming off the back end of the detectors in the Large Hadron Collider is tossed because it's not of interest. It'll be very similar to the way the astronomy community is going to work with the square arrays coming online in the Southern Hemisphere, where the vast majority of the data coming off the square arrays will be tossed because it's not of interest. The idea is to move into a mode where you only save what you need because it's so easy to recreate it. And so this is another way that the speed of the system, its ability to generate truly massive ensembles, and the fact that rerunning is actually cheaper than saving. These are all distinctive features of this system. Now, when I started work with Nvidia, and this originated from the conference that Philip alluded to at the top of the hour, a meeting that we held in Aspen last year that I co-chaired with Veronica Eyring. At that time, FourCastNet was only able to run out to about 45 days without blowing up. That's changed. They're now able, they've transformed the system from doing Fourier transforms in a rectilinear space to Fourier transforms using spherical harmonics and an appropriate basis set for the sphere. And that's now allowed them to get up to 90 days. In fact, now these slides become outdated almost week to week. As I mentioned to you earlier, they're now up to 3 times that. So this is essentially a community milestone. It allows them to now transition from looking at typical weather prediction scales to subseasonal to seasonal forecasting. So they've gone from NWP now into a world where we can transition from weather scales now to beginning to look at the intersection of weather and climate. And that transition occurs quite literally at the 2-week timescale. Why? 2 weeks is when you lose predictability due to error growth in the Euler equations. It's also commensurate with the radiative convective equilibrium timescale, which sets climate. That's the timescale at which the radiative diabatic heating rates in the atmosphere come into equilibrium with precipitation. So climate is to the right-hand side of this graph, which is where RCE is, king of the hill, and weather is on the left-hand side of this graph. They intersect at 2 weeks, And we're now able to penetrate through that 2-week barrier using ForecastNet and start to look at the interplay between weather and climate. So quite an interesting time. And this is important because a lot of the impact work that we need to do for looking at extremes on longer timescales obviously is in the S2S timeframe. For example, we're going to have a particularly strong hurricane season in the Atlantic. That's an S2S question. And so the ability now to operate in that space becomes really a transformative capability for us because of the ability to emulate numerical weather prediction accurately and at vastly higher speeds. So let me talk a little bit about the speed of the systems, as I've been alluding to that. This shows you the peak number of samples being generated per second as a function of the number of GPUs expressed in binary on the horizontal axis on a variety of different computers. So joules, a machine called Perlmutter, which is number 5 on the top 500 list. That machine is just down the hill from me. That's a Cray. And then another machine called Selene. We've been able to attain 150 petaflops in mixed precision on that machine, which is very, approaching, which is a very high percentage of peak. And it's really a remarkable attainment. This code is exhibiting, the fact that it's exhibiting straight line behavior on these graphs, and these are log-log, is what's known as strong scaling, which means that the time to solution is decreasing with the number of compute cycles you throw at it. And that's most definitely not true of traditional NWP, which stalls on large number of nodes. This code is exhibiting spectacular strong scaling. NWP exhibits weak scaling. This is strongly scaling. And it also you can train it really quickly. So this is also a feature we want to be able to train the code on timescales of hours. If you want to use it in an operational context, and that's attainable as well on sufficiently large amount of compute power. And this makes it useful potentially for operational purposes. We need it to be trainable in hours, not timescales of days, if you wanted to, for example, look at what's going to happen tomorrow. And that's possible now with this system. So I'm very close to drawing to a close here. I think the future for this code is really quite exciting. I've been describing a world in which we are operating at 25 kilometers. Nvidia is asking what could we do if we went to the aspirations in the EU of constructing digital twins. And I'm delighted that the EU has taken such a global and leading position on creating digital twins, and the rest of the world, including the United States, is playing catch up with the EU. But Nvidia is asking the question, could we get to models that can run at 1 kilometer length scale horizontally? And that means increasing the number of horizontal grid points to roughly 500 million. The Earth's surface is tiled by 500 million square kilometer tiles. And the beauty of the Fourier transform, and this is the other key reason why the Fourier transform is so important, is that most techniques that are used in the machine learning community scale like a polynomial in n. So anything that scales like n squared is a problem. Once you're looking at going from 1 million to 500 million grid points, the beauty of the Fourier transform is that it scales like n log n. And so that's roughly linear. And again, that is a transformatively enabling capability to get to ultra high resolutions. And this is, again, something that NVIDIA is beginning to probe, and I think is actively working with some of the leaders of the digital twin efforts in climate in Europe to explore the feasibility of this approach with them. And again, I'll leave you with the fact that we can generate, currently generate ensembles 100,000 times faster at 1/10,000th the power requirements of traditional NWP. So again, let me remind you, this talk would not have been possible without all these wonderful colleagues. including some that I've had the pleasure of training. We have a very exciting future. We collectively, meaning the climate community, have a very exciting future in front of us as we think about pairing machine learning with NWP. We're now at the point, as I've mentioned, of being able to go to quite high, very fine length scales and to transition from looking at weather with these systems to looking at climate and beginning to explore other components of the Earth system. And at the same time, making sure that we are faithful to the underlying equations. This is something that there's no reason in doing this if we're violating laws of physics. And so this is something where, we've been discussing this actively with our colleagues at Nvidia. And the last thing I want to leave you with before ending and taking your questions and moving into a dialogue with all of you is that this would not have been possible without a transformation in the way that the academic community and the traditional climate and numerical weather prediction communities are working with industry. And so industry in the past has been, a really phenomenal partner in terms of creating, excellent hardware, really helping us think through how to take compute to the next level. Thanks to machine learning being as lightweight and agile as it is, we've now seen the industrial community and the private sector move into a leadership role in many cases on machine learning. And in Nvidia's case, actually standing up a climate group in-house, including experts trained by some of the leaders in the climate community, and they're now inside Nvidia. And so what has now happened is that the industry has become a full-fledged intellectual partner with the climate community because we have partners on both sides of the equation. And that is, again, a very exciting development. It's a relatively recent development. The people inside of Nvidia are determined to get the right answer for the right reason. And so we've been, one of the outcomes of the conversation that we had with them last year in Aspen was a set of conversations around making sure that we were solving the fluid equations correctly. And they took that suggestion on very seriously and are probing that. So I'm confident that what I'm showing you is, our goal is to be faithful both to the underlying equations, but also be useful. And with that, let me conclude and take any questions you might have. Thanks very much for your attention.
Bill, thanks a lot for the talk. This was really great. But I think Duncan will moderate the questions, so I'll just pass on straight to Duncan.
Absolutely. Thanks for the great talk, Bill. It's really fantastic overview of this exciting new technology and kind of way of doing things potentially. I'll just dive straight into the questions from the neural network in mind of the time. I'll start with the latest one first. So from Peter Watson, the results are certainly very interesting. When it comes to predicting risks from extreme events, the most relevant are typically those with return periods of several decades or more. The events you showed, the results are ones less severe than this, I think, where there'd be already some training examples in the data set. How confident do you think we can really be that the model will simulate extreme events realistically? And this is something I wondered actually while I was watching the talk. How, if I may kind of paraphrase as well Peter's question, how confident are you that the model is able to explore parts of the attractor it's never seen, right?
That's something where we will the way that we're going to have to probe that question. Initially. Duncan and Peter, is going to be expensive. We're going to have to run reasonably large ensembles of a conventional climate model in parallel with the huge ensemble to understand whether or not we're getting the right answer for the right reason. So initially, there's going to be some extremely expensive work that we're going to have to do on the front end to trust the system. I think one of the reasons, though, that I introduced this driver framework earlier Duncan and Peter, is to move off of looking at the events themselves and looking at the causal mechanisms, because there we can sample the statistics and their characteristics much more readily, and then it becomes a question of understanding the probability of co-occurrence and spatial coincidence. That transforms the problem slightly, but it does mean that the causal mechanisms are much more subject to much better statistics than we would have been otherwise. So I'm trying to transform this problem off of having to get everything right to, okay, fine, let's get the drivers down, because those we can get great statistics on, and then we reduce the problem to getting co-occurrence and coincidence. That's, I think, an easier problem.
So actually, that really nicely leads on to the next question, which was the first question from Michael Spicer. How does this framework, this causal framework, require assumptions about independence between the drivers, or do you need to make any assumptions on that?
You do not, and but I will say that you very quickly crater anything except Gaussian statistics. But if you allow me to use Gaussian statistics, then it's easy to build to look at the joint occurrence probability, including cross correlations, in a Gaussian framework. That is not generally true once we abandon Gaussian statistics. But if we abandon the null hypothesis that the system is truly uncorrelated, then the next thing we would begin probing would be Gaussian statistics. And then if we need to relax off of that, I've been actively working with my group here on using fast kernel density estimation for probability distributions. We have systems that work up to a few dozen dimensions that can be trained very quickly. So we can even abandon Gaussian if we have to.
That's good to hear. There was a slightly more technical question from Agnew Singupta on how you generate the ensemble members. What are you sampling from? What are the sources of perturbation?
So the sources of perturbation are noise added to the both introduced into the initial conditions and also injected into the system itself. But the usual way of generating an ensemble in an NWP model is to perturb the initial conditions at the level of machine precision. And so in a conventional NWP, you will see the solutions begin to separate after approximately 100 time steps. And that's true of this system as well. So it doesn't take long for this initial condition uncertainty to begin manifesting itself, and we also inject noise into the network as it operates.
Okay, yeah. I mean, yeah, that's interesting. And there's also opportunities, presumably, to do that on the hardware level with the lower levels of precision that some of the GPU chipsets work at.
That's right. Correct, Duncan. Yeah, my second go round with trying to beat records with GPUs. The first time around, we did this by using on training using 16-bit arithmetic on a machine at Oak Ridge, and we're using 32 and 16-bit arithmetic for this system as well, because that does provide you with speedups of factors of 4. So, and precisely because you're doing that truncation, you're introducing noise at the least significant bit, which for single precision at levels of 10 to the minus 7, that will grow very rapidly.
Okay, thank you.
Great. So there's a question from Alex Rybchuk, and I had a slightly related question which I tag onto it, and this is about sort of the resolutions. So how difficult would it be to repurpose the sort of global scale network here at 25-kilometer resolution to make it a 1-kilometer resolution model? You touched on this briefly already, but I wondered about the same thing too when you train on ERA 5 in relatively high resolution and you want to apply this to sort of high res MIP, which isn't just really high res enough. No. Do you have some insights for us on how you deal with resolution differences between training and application, and in particular go to lower lower resolution application data or high resolution data in the kilometer scale?
The only, so this is something I'm not going to go out on a limb here. Philip, great question. There's very little in the way of 1 kilometer data out there, if you think about it. The only global 1 kilometer data sets we have are from satellites. Now, I just happen to have collected all of the data from NASA's sounders at 1 kilometer resolution for the last 25 years. I have that sitting here in its raw form, and it's hyperspectral. So we could train that network against satellite data if we built a satellite emulator for it. That if you wanted to do this right this minute and do it against the real world, you'd have to go and use satellite data to pull that off, because that's the only data, that's the only true data that we have. The Diamond consortium that's been set up by Bjorn Stevens and others is running at sort of 3 kilometer-ish resolutions and snapshots of about a month or so, as you're well aware. And there have been a couple of trial runs of the Diamond framework now, but those data sets are too short to serve as training data sets for the system. The only thing that has the adequate length is literally the same data that goes into. So let me invert your question slightly, Philip. What is the value of ERA5? The value of ERA5, ERA5 is based on yet another. Effectively, it's based on another climate model. The reason why it has value is that it's been constrained using a simulation. 99.9% of the data going into that system, in terms of bulk, is coming from satellites. So the reason why we train against that system is because it's been constrained against satellites and also ground radar. Well, in that case, if you want to train high-res right this millisecond, you go back to the source. The source are atmospheric sounders. And I need to talk to my Nvidia colleagues, but I'm sitting on all that stuff right. I have all of it here. And so we didn't need to, yeah. So that would be quite an ambitious project, but it's doable.
That sounds fascinating, and you sit on a lot of data. You must have a bigger computer than I do, for sure. So this was a really great talk. Great questions from the audience. Apologies to you and everyone else for the technical glitches, but we recovered quite nicely, and we got a really nice talk for that. I think the neural network is back up and people can meet there. I'm not sure how many people swapped to YouTube or not, but you can join Bill and answer more questions if there are people still on there. I haven't had time to fully check on that. And I should maybe just thank you again, Bill, and also remind people that we are back in 2 weeks and we have a talk on AI predictions of the Indian summer monsoon with Ravi Nanjundia, which I apologies couldn't pronounce properly. And so we look forward to see you all back. Thanks, Bill.
Thank you, Philip. And before you go, could you post where would I find the instructions on hopping onto the neural net?
We'll put that in the chat shortly.
I appreciate it. Thank you. Thanks everybody for joining, and great questions from all of you. Look forward to following up with you at some other venue. Thank you.
Great. Thanks, Bill.
Thank you. Bye-bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
AI is a powerful tool.
summit can help ensure that artificial intelligence charts a course that benefits humanity and bolsters our shared values.
My name is Anna.
AI is a powerful tool.
Bye.